Hello, everyone. Thank you so much for attending this presentation. My name is Paul Fady, and I'll be giving the talk today. As you can see, it's a collaborative effort by many people, but I am privileged enough to be here in Sendai with all of you in-person attendees to talk about our project entitled Sequestration of Multi-Drug-Resistant Clinical Bacterial Isolates by Precision-Engineered Waste Lignocellulosic Biochars. Now, that's quite a long title, and I'll break it down. Basically, what it means is that we're taking walnut shells, which are a waste stream of lignocellulosic biomass. We're pyrolyzing them into biochars, and then we're using those biochars to filter active pharmaceutical ingredients, APIs, out of wastewater and clinical uh, bacterial pathogens through the walnut shell. And the aim of the project really is to address antimicrobial resistance, or AMR. Now, that's my subject of expertise, and I know that this audience maybe is not quite so well versed in AMR, given that it's a waste conference. So I'll talk now a little bit about what AMR is. So AMR is a completely natural phenomenon by which bacteria develop the ability to survive in the presence of compounds which would have previously killed them. So in the case that we're considering here, we're talking about antibiotics used by humans. And in fact, the overuse and misuse of antibiotics is the biggest driver of AMR. And AMR subsequently results in drug-resistant infection. Antibiotic-resistant bacterial infections caused 1.3 million deaths per year in 2019, and they were associated with 5 million deaths per year, and that's from the Graham report by Murray et al., which is the sort of seminal piece of data that we have right now on the burden of disease caused by AMR. One aspect of AMR which is less well studied, although it's becoming more and more of a prominent part of the field, is the environment, and in particular the way in which waterways promote AMR. They act as a reservoir for resistant bacteria, they act as a source of active pharmaceutical ingredients, and the environment is a location where those two can meet and where selective pressures can be applied. Now, the World Health Organization considers preventative measures of controlling AMR, such as, in our case in particular, sanitation, wastewater and sewage treatment, equally as important as antibiotic drug development, if not more so. So that's the angle that we've taken in this project. Something which probably needs a bit less introduction for this particular audience is lignocellulosic waste, which is lignocellulosic biomass waste, which derives mostly from agriculture and forestry industries. Some examples are sawdust, wood chippings, nutshells are what we're particularly considering in this project. And biochars, which are the thermal or thermochemical decomposition products of lignocellulosic biomass. Biochars have been applied to filtration for pollution prevention in the past. That's not a completely novel idea. I put a few examples up here of some papers, some more, some less recent, using pistachio shell biochars to filter out antibiotics, straw biochars to remove bisphenol A, and biosolids or sludge biochars for triclosan sequestration. But all of these publications, as fantastic as they are limited in one way or another, and we sought to really address some of these limitations with our methodology in this study. There are really 5 things that make our approach for this particular study novel. We were very keen to use clinical multi-drug-resistant bacterial isolates because many of the existing publications in the literature use lab strains like E. coli K12, MG1655, or DH5 alpha, which are both very commonly used lab strains, but which have no relevance to human infection. We made sure to use bacterial isolates which have come from patients and which are of bacteria which the World Health Organization considers to be priority pathogens. So they're on the WHO's list of critical priority pathogens. We removed both bacteria and APIs. Many publications are out there in which APIs are removed and quantified very, very well, but that's it. There's no consideration of the microbiology at play. So we really wanted to cover both sides because they're both very important in AMR. We have extremely precise production conditions. On the engineering side, many publications in the literature use commercially available activated charcoal, for instance, and the production conditions are not at all defined. So, we dug into it quite a bit, and sometimes it'll just be like, you know, this particular wood, was subjected to 1,000 degrees Celsius for 6 seconds, and obviously that doesn't produce a particularly homogeneous sample. Sometimes the wood type isn't even specified, so really you have some very poorly defined production conditions for your biochars. Ours are extremely well defined, and that allows us to correlate production conditions with performance. We use real wastewater rather than synthetic wastewater, which is maybe sounds like a small consideration, but again increases the real world potential and applicability of our results. And we have some powerful analytical techniques which allow us to suggest mechanistic underpinnings. And all of this derives from an interdisciplinary collaboration between microbiologists, chemical engineers, and analytical chemists. This is the ultimate aim. We would like to develop engineered biochar filters to put into sink traps, into shower drains in hospitals, for instance, to sequester both the active pharmaceutical ingredients that you might find when someone is using, for instance, an antiseptic body wash, but also the drug-resistant bacteria that are coming off their bodies, which are very common in hospitals. And we think there could also be some applicability in manufacturing plants for pharmaceuticals, outflow pipes to try and sequester APIs before they ever make it into wastewater treatment plants and into waterways. Very briefly, this is our workflow. I won't spend too much time on it, but effectively we mill our walnut shells down to 1 to 2 millimeter particles, and we either pre-treat them with an NaOH solution, an alkaline solution, or we don't. We then dry them and pyrolyze them in this nifty reactor built by Dr. Meredith Barr, my colleague and collaborator on this project. And really the way that we do the experiment is that we put the adsorbate above this bed of biochar, and then we spin it down in a centrifuge, and we measure before and after. So for the wastewater, that's exactly what we did, and the measuring was done with tandem mass spectrometry system. For the bacteria, it's a slightly more lengthy process whereby we culture the bacteria first, pelleted them, resuspended them in saline, plated them out after a serial dilution to do a colony count, spun them through the filter, and then subsequently did a colony count afterwards to look at before and after. So it's a very simple process, really. Let's get into some results. These are results showing the sequestration of multidrug-resistant bacteria. So we have Staphylococcus aureus EMRSA15 on the top, and Pseudomonas aeruginosa RP73 on the bottom. In blue are untreated biochars, and in red are alkaline pre-treated biochars. And you can see that Staphylococcus aureus EMRSA15 was sequestered better by pre-treated biochars. So in red you have higher numbers for the top, and Pseudomonas aeruginosa RP73 was sequestered better by untreated biochars. So in blue you can see that you have higher numbers for the bottom on left versus right. So this is interesting in that we can see that production conditions really do affect the ability to sequester bacteria. We still get up to 94% removal of RP73 and 85% removal of EMRSA15, which is fantastic. And you can see that broadly increasing temperature correlates with ability to sequester bacteria, which is something that we'll come back to. But pretreatment and peak pyrolysis temperature both have an effect on walnut shell biochar's ability to sequester bacteria, and we get good sequestration ability in some conditions, which is fantastic. If we look now at APIs, these are the 22 APIs deuterated APIs that we added to our wastewater to measure before and after using our mass spectrometry method. And you can see that it really varies how well these biochars can remove APIs. So on the far right, we see methylphenidate is removed at very, very high levels, up to 94%. And on the far left, benzoylecgonine, which I believe is a cocaine metabolite, is removed relatively poorly, around 40% removal. The darkness of the band correlates with, represents the peak pyrolysis temperature, so the darker, the higher the peak pyrolysis temperature. In blue is untreated, and in red is pre-treated. So you can see that there's not consistently higher bars in blue than in red, so it's not that the pre-treated is always better, or the untreated is always better than the pre-treated, or vice versa. It really depends on the specific API and the specific biochar. If we look a little more closely, we can see that overall there's no significant difference in the amount of API removed between untreated and pre-treated biochars, but the difference really lies in the type of API that's removed. So this graph there is just to show that there's really no difference on average across all compounds. But hydrophilic compounds, which have a negative log P, like metoprolol and MDMA, were sequestered better by pre-treated biochars. So you can see the red bars are higher than the blue bars, but hydrophobic compounds with positive log P, like morphine and clarithromycin, were sequestered better by untreated biochars. And you can see that clarithromycin was really the only antibiotic that was well removed. Trimethoprim and sulfamethazine, which have been shown in other studies using other feedstocks to be removed quite well, weren't for us. But so we can see here that the nature of the chemistry of the API and the nature of the chemistry of the biochar really does matter in removal. And I was talking earlier about higher peak pyrolysis temperatures, broadly meaning that there's better removal, and we can see here through the SEM images that this is likely because the pit membranes rupture during pyrolysis. And that may be explained by a buildup of internal pressure caused by volatilization of organic compounds, which increases surface accessibility. So we think that basically the hotter it gets, the more the gas rips apart the biochar and the more surface area that allows. We've got a lot more SEM and analysis in the paper that we've got under submission right now, but given the time, that's all I'll go over for today. So in conclusion, waste lignocellulosic biochars show excellent adsorption efficacy for both APIs that exert selective pressures and the MDR bacteria that are subject to those pressures. The higher the peak pyrolysis temperature, the more effective the removal, likely because of increased surface accessibility. Untreated and pre-treated biochars remove different types of compounds with a range of chemistries, so an inline filter for a hospital sink or a shower trap could leverage this using a blend of biochars. In the future, we'll have to consider what we do with the biochars after they've been used as filters, maybe repyrolyze them or burn them. But these results represent a promising development towards waste valorization for pollution prevention in the context of AMR mitigation and One Health. We're very excited to keep taking this forward. Thank you very much for your attention, and I'm happy to answer any questions.